So right now we're going to do an overview of elevator forces and motion. So right here on the left side of this slide, I have a picture of an elevator that has a cable pulling up on the elevator and a passenger inside of the elevator. For all of these problems, I'm going to be focusing on the forces and motion of the passenger, which is why I drew my system boundary around the passenger. So I'm going to start off with a velocity time graph for 8 different motions of that passenger while they're in an elevator. And then from there, I'm going to go to the acceleration time graph that corresponds with it. Now, this velocity and acceleration time graphs actually could be used to just talk about the motion of the elevator itself instead of the passenger if that's what the problem we're asking for. But when it comes to the forces, I'm going to be focusing on the forces acting on the passenger. So the 8 motions I'll be focusing are when the elevator is at rest at the bottom of an elevator shaft, when it starts to go up, when it is going up at a constant speed, when it is slowing to a stop at the top, when it is stopped at the top, when it starts to go down, when it is going down at a constant speed, and then finally, when it is slowing to a stop at the bottom. Now, if that's what the elevator is doing, that too is what everything within the elevator is doing, notably the passenger. So we're going to construct the velocity time graph first. When it's at rest, the velocity would start off at 0, and then it would remain at 0 at every instant in time while the elevator is at rest. When it starts to go up, it starts off from a velocity of 0, and then it speeds up. The velocity increases as time goes on. Oh, and just to be clear, I'm defining up as our positive direction here, which is why positive velocity corresponds with an upwards motion. Conversely, a negative velocity would be a downwards motion. Anyways, the third motion here is when it is going up at a constant speed. So after the elevator and all of its contents have accelerated to whatever its maximum speed is going to be. At that point, the speed remains constant. So whatever velocity we ended at in the previous region is now going to remain constant for the entire duration of time while the elevator is going up at a constant speed. And then when it is slowing to a stop, the velocity approaches a velocity of 0. That's why we're seeing this downward slope. When the elevator is stopped at the top, the velocity is 0. The elevator is not moving, it is completely stopped, and it will remain at a velocity of 0 until it starts to move again. When it starts to move down, it goes from not moving, a velocity of 0, to moving, a non-zero velocity. But because it's going in the opposite direction, we're going to have that negative velocity. Once it reaches its maximum velocity while moving down, it will remain at that velocity at every instant in time while it is moving at that constant speed. And then when it's time for it to slow to a stop, once again, the velocities will approach 0 until such a time that the elevator comes to a complete stop. These are the ways that we can represent our velocity at these 8 different motions of an elevator and its contents. Now, to construct the acceleration time graphs here, we're going to be looking at the slopes of a velocity time graph because the slope of a velocity time graph is acceleration. So while the elevator is at rest at the bottom of the elevator shaft, we have a perfectly horizontal line on our velocity time graph. So we have no slope, which means there is an acceleration of 0 when the elevator is at rest. When the elevator starts to go up, we have that positive slope on our velocity time graph, so we have a positive acceleration during that time. When the elevator is going up at a constant speed, that is a horizontal line on the velocity time graph, or a slope of 0, which means the acceleration returns to 0 in this region. When the elevator is slowing to a stop at the top, we have a negative slope on the velocity time graph, so we have a negative acceleration on our acceleration time graph. When the elevator is stopped at the top, That's a horizontal line on the velocity time graph. So that's an acceleration of 0 on the acceleration time graph. When the elevator starts to go down, it's a negative slope on the VT graph. So it's a negative acceleration. Going down at a constant speed, horizontal line on the VT graph, 0 acceleration on the AT graph. And then finally, when it's slowing to a stop at the bottom, we have a positive slope on our VT graph, so we have a positive acceleration on our AT graph. So right now we have our velocity and acceleration time graphs set up to represent the motion of an elevator and its passengers. At this point, we can now use the acceleration time graph to help us construct qualitative force diagrams for all of the forces acting on the passenger. So, when the passenger is at rest at the bottom of the elevator shaft, we have the force of gravity acting on the passenger, and we have the interaction between the elevator and the passenger, that floor pushing up on the passenger. Here, you'll notice that the force normal and the force gravity were drawn the same length. That means these two forces are balanced, which means the sum of the forces should be 0. And that should make sense because we have 0 acceleration, which from both Newton's first and second law of motion should allow us to state that the forces should sum up to 0. So sigma F is equal to Fm minus Fg, and specifically here, sigma F should be 0. Now, I'm still writing it as ma for sigma F and mg for Fg, but just know that the acceleration here would be 0, so if you plug in 0 for that a, regardless of what the mass of the passenger is, some of the forces should still be 0. Now, when the elevator, and by extension the passenger, start to go up, we have a positive acceleration. So our force diagram is going to look a little different. We still have the same amount of force gravity, because we calculate that by taking the mass and multiplying it by the gravitational field strength. Neither the mass nor the gravitational field strength change, so Fg remains the same. However, we need to show that we have a positive acceleration, or a sum of the forces pointing upwards. To do this, the force normal would have to increase, to be pushing the passenger up. That would allow them to accelerate upwards. We still have the same sum of the force equation. It's still the same two forces acting on the passenger, and we can still write it with ma equals Fm minus mg. It's just here, ma would be some positive value that would indicate an upward sum of the force and an upward acceleration. Once the elevator and the passenger reach that constant speed, we return to that same force diagram we had when it was at rest. The force normal would have decreased until it was balancing out the force gravity. Once again, note, the force gravity has not changed, and neither have the sum of the force equations. We have the same sum of the force equation for these first 3 motions, and actually, we'll have the same for the remaining 5. We only have the force gravity and the force normal acting on the passenger in each of these motions. The force gravity does not change. The force normal does, in order to produce those accelerations we're seeing on our AT graph. When it's slowing to a stop at the top, our force normal would have to decrease to allow a downward acceleration. When it's stopped at the top, forces are balanced because the acceleration is 0 again. When we are starting to go down, downward acceleration, less force normal than force gravity. When the elevator and the passenger are going down at a constant speed, forces are balanced, and the acceleration is 0. And then finally, slowing to a stop at the bottom, we have a larger force normal than our force gravity, and that is explaining the upwards acceleration. Note, every single one of these force gravity vectors is drawn the same length. The m and the g, the way we quantify our force gravity, does not change. The acceleration does change in each of these 8 motions, which means the force normal is what is fluctuating in order to account for that upwards, downwards, or 0 acceleration. So when it comes to our elevator forces in motion, the weight, that force of gravity, does not change at any point during the passenger's ride up and down the elevator. The passenger accelerates along with the elevator because the force the floor exerts on the passenger, the normal force, varies. This sum of the force equation is how we can solve every single elevator force and motion problem when we're looking at the forces acting on a passenger. If we were to look at the forces acting on the elevator itself, we would still have a force gravity for the elevator. And then we would have the force tension rather than the force normal. But it would still be the same concept, where the weight does not change. The acceleration changes, as does that upward force.